In this lecture, we will discuss logic operations. A digital system consists of a combination of circuits which are connected in some specific ways, like to perform a specific function. Okay, all the variables are involved in this system. In particular, two-value discrete systems are known as binary systems. So if we have a system which has only two values allowed in the system, we call it binary system. And of course, we know that those two values are 0 and 1. Logic operations are important in order to translate a word statement. We want to describe a problem. I need a circuit that does this specific task. It's a word statement. In order to translate this word statement to a digital logic network, we need to know logic operations. Okay, and of course, these logic functions only operate on variables that are allowed, and there are 1 and 2. So let me write it down for you. Logic operations are important in translating a word statement to digital logic network. These logic functions operate on variables that are allowed only two values. Those values are 1 or 0. So in a circuit, like if we show a switch, if the switch is open, we say X is equal to 0. When the switch is closed, we say X is equal to 1. Two states of the switch. Okay, there is an easy way to describe a function which is using a table known as truth table. Truth table. Okay, we use this table to describe functions. Okay, this table lists the output values for all possible combinations of the input. So what does the truth table do? It lists the output values lists the output values for all possible combinations of the input. Okay, I think that I lost the connection. So let me repeat. I said that to describe a function, we use a table called truth table, and this table lists the output values for all possible combinations of the input. Okay, what functions do we have? The first function we want to learn today is called AND function. AND function, f of a and b is equal to a dot b. Or we can show it with a, b. Okay, the symbol for AND function is like this. It has some input and one output. Here in this example, we have two inputs, but it can have like more than two inputs. So input A, input B, and the output is A, B. The truth table for AND function is like this table. The inputs are listed on the left, and on the right we have the output. We write all possible combinations for the input. So we have 0, 0, 0, 1, 1, 0, and 1, 1. The output of an AND gate is 1 only, and if only all the inputs are equal to 1. So for 0, 0 is 0. If A is 0, B is 1, because one of the inputs is 0, the output is still 0. If A is 1, B is 0, again the output is 0. The last combination, because both inputs are 1, the output is equal to 1. So this, I repeat, the AND function output is 1 if all the inputs are 1. The next function is OR function. Okay, by the way, we call this symbol as AND gate. So the physical device which implements the AND function is called AND gate. So for OR function, we show the OR function in this way. F of A and B is equal to A plus B. So this one is OR function. The symbol and gate for OR function is like this. We have input on the left and output on the right, and the truth table for OR function is here: A, B, A plus B, 0, 0, 0, 1, 1, 0, 1, 1. Okay, what is the output of an OR function? The output of an OR function is 0 only if all the inputs are 0. Other than is equal to 1. So if we look at these input combinations here, we see that only for the first combination, all inputs are equal to 0. So, oh, sorry, yeah. So I said that the output is 1 or if all the inputs are 0. It was wrong, sorry. The output is equal to 0 if all inputs are equal to 0. So the only time that the output is equal to 0 is when all the inputs are equal to 0. The output is 1 if at least one each input is equal to 1. So for the first combination, because both inputs are 0, the output is 0. For the other combinations, because we see that at least one of the inputs are equal to 1, the output is equal to 1. Okay, so this one is for the OR gate. So in OR gate or OR function, the output is 0 only if all the inputs are equal to 0. So this one is an OR gate. Okay, the next gate I will talk about it as NOT gate or NOT function. NOT function, we show the NOT function in this way: f of a is equal to a bar or a prime. The prime and bar both have the same meaning. It means like a complement, okay? And the symbol for OR gate is triangle with a small circle and the output, and it has one input and one output. If the input is A, the output is A bar or A prime. Okay, so this gate has the equal number of inputs and outputs, and the truth table for NOT function is A or A bar. If the input is 1, the output is, if the input is 0, the output is 1. If the input is 1, the output is 0. The next gate is Nand function. Okay. So what is the Nand function? Nand function is a function that is identical to the AND function with the output inverted. So Nand function is same as AND function with the output inverted. And we show it in this way: f of a and b for NAND function is AB, which is AND and inverted. So we can say f of AB is a function that is identical to the AND function with the output inverted. Okay? So in other words, we can say the NAND function is a combination of AND function and NOT function. How we show a NAND gate? Here is the symbol for NAND gate. Inputs are A and B, and the output is AB bar. If we like expand or extract this function, we can tell that this NAND function is equal to an AND gate and inverter. So AB bar. So these two are exactly identical. And the truth table for AND function, for NAND function, let's just find it. So if we have A and B, which can be 0, 0, 0, 1, 1, 0, 1, 1, Now let's show the AND of this function. For AND, we know that the output is 1 if all the inputs are 1. So it's AND function. And the NAND function is complement of AND function. Okay, so this one is a NAND function. So if I'm supposed to like uh, describe the NAND function based on the inputs, I would say the NAND function gives the output of 0 if all the inputs are equal to 1. Here. The next gate is null function. Null function. We show this function in this way: f of a and b is a plus b bar. And exactly, it's an identical to an all function with the output inverted. Okay, so we can say a null function is a combination of an all function followed by a not function. So the symbol for NOR gate is like this. Inputs are A and B, and the output is A plus B bar. It is identical with OR gate followed by a NOT. Okay, so this one is NOR gate, and the truth table for NOR gate is here. We have inputs A and B. 0, 0, 0, 1, 1, 0, 1, 1. All gate, this part, we know that the output is 0 if all inputs are 0. So it's 0, 1, 1, 1. And the NOR gate is inverse or complement of OR gate. So it's 1, 0, 0, 0. So if I want to describe NOR gate as a function of inputs, we can say the output of a NOR gate is 1 if all the inputs are equal to 0. Other than, the output will be equal to 0. Okay, the next gate we want to describe, it's called exclusive OR gate. Or we show it with XOR function. Okay. We show this function in this way: f of a and b is equal to a. This one is a symbol for XOR function. A circle with a plus sign in it, b. If we want to represent XOR function in a term of and, or, and not, we can say XOR of A and B is equal to A bar B plus A B bar. So this one is XOR function. So it has one output, and so it's the output is one if if an odd number of the inputs are one. So the output of XOR gate is one if and only if an odd number of the inputs are equal to one. So let me write it down for you. XOR has an output of one if and only if an odd number of its inputs are one. So if we have two inputs, the output is one. If one of the inputs is one, the other one is zero. Okay, the gate, the symbol for XOR gate is here. This one is symbol for XOR gate. It's A, B, and the output is A, X, or B. Okay, and if we want to show the truth table step by step, the first thing we know that here is A, B, 0, 0, 0, 1, 1, 0, 1, 1. And the last step is like XOR of A and B, which is A bar B plus A B bar. Based on the definition, we know that the output is one only and only if one of the number is like odd number of the inputs are equal to one. So for two inputs, the odd number means that only one input is equal to one. So we can definitely say that for 0, 0, there is no odd number of the inputs equal to one. So it's 0. For 0, 1, the output is 1. For 1, 0 is the 1. And for 1, 1, because we have even number of 1s, so the output is 0. Okay, so this one is the XOR gate based on the like input. But if we want to show this truth table in detail for XOR, we can just write it like this to show the details of this calculation or relationship. So A bar, B bar, A B bar, A uh, A bar B and A B bar. Okay, let's just find these values. So A bar, third column, A bar is the complement of A, so it's 1, 1, 0, 0. B bar is 1, 0, 1, 0. A bar B, A bar B. So it's and. So A bar B is because it's and, it's only it's equal to one if both inputs are equal to one. So A bar B for 0, 1 is equal to 0. For 1 and 1 is equal to 1. For 0 and 0 is equal to 0. For 1 and 0 is equal to 0. So this one is A bar B. Okay. And what about A B bar? A B bar. So we consider these inputs. So A B bar is equal to 1 if both A and B bar are equal to 1. So A B bar is 0, A B bar is 0, AB bar is 1 and AB bar is equal to 0. Okay, and the last column, let's just fill it this complete this column again. So we want to find AB bar, A bar B plus AB bar. So we want to find A bar B and AB bar connected together with an OR gate. So we know that the output is 1 if at least one of the inputs are equal to 1. So we can say, because here both the inputs are 0, output is 0. Here one of the inputs is 1, output is 1. Here one of the inputs is 1, and here both inputs are 0, so it's 0. So here we are showing the truth table of XOR gate in detail. Okay, but without we didn't have to write all this like middle point calculations, because based on the definition of XOR gate, we know that the output is 1 if the odd number of the inputs are equal to 1. Okay, the next gate we want to learn today is exclusive NOR function or gate. Exclusive NOR or X NOR function. Okay, the XNOR is the inversion of XOR. So we can say f of A and B is the complement of XOR, which is the complement of AB bar plus A bar B, which is equal to AB plus A bar B bar. Okay, and the symbol for XOR gate is like this. It's like XOR with a circle in the output. So it's A, B, and the output is A, XOR B. Also, we can show it with this symbol, like a circle with a dot inside it. So it's like the same as the symbol for XOR gate. So the truth table for XOR gate is here. A, B, XOR, and XNOR, which is like complement of XOR. If AB is 0, 0, 0, 1, 1, 0, 1, 1, XOR is 0, 1, 1, 0, XNOR is 1, 0, 0, 1. So for two input gate, we can say that the output of an XOR gate is 1 if both inputs are same. For XNOR, XNOR. For XNOR gate, we can say both the output is 1 if both inputs are same. Okay. So we learned all basic functions and gates, and now it's time to learn Boolean algebra. Okay, in order to do some modification, calculations, on Boolean functions, we need to know the Boolean algebra. Okay, so we want to talk about Boolean algebra. We have some postulates for Boolean algebras that I'm writing here one by one. Postulate 1 says that x, the variable x, all with 0 is equal to x. Variable x and with 0 is equal to 0. Variable x and with 1 is equal to x, and the variable x all with 1 is equal to 1. Okay? P2, postulate 2, is called operations are commutative. So x plus y is equal to y plus x. Okay, so this plus signs and this x dots that you see here, they are not arithmetic like plus and multiplication. They are and all. Okay, they are not plus or multiply. So they represent and all function. Okay, and of course we know x dot y is equal to y dot x. Okay, P3 is called distributive. And it says that x times y plus z is equal to x dot y plus x dot z. And x plus yz is equal to x plus y dot x plus z. Okay? Postulate number 4 is called associative. And it says that x plus y plus z is equal to x plus y plus z. You see that we move the parameters from y and z to x and y. And also we can say x dot y dot z is equal to x dot y dot z. Okay, and postulate number 4, number 5. Number 5 says that any number, any variable all with its complement is equal to 1, and any variable ended with its complement is equal to 0. Okay, it's very important. But then after learning these postulates, we want to learn some theorems. These theorems help us to minimize the logic circuit. So in order to minimize the logic circuit, we need to use some theorems, the Boolean theorems that I will introduce them here. So theorem number 1, which is called Law of Idempotency. Law of Idempotency. And it says that x plus x is equal to x, and x dot x is equal to x. So if you AND or any variable with itself, the result is the variable. Theorem number 2, is called Law of Absorption. And it says that x plus x dot y is equal to x, and x dot x plus y is equal to x. So this one is law of absorption. The third theorem is law of evolution. And it says that if you complement a variable 2 times, it will be equal to the variable itself. So x bar is equal to x. The fourth theorem, which is the most important one, is called De Morgan's law. Okay? And De Morgan's law implies that any function can be complemented by changing the ors to ands to ors, and then complementing each of the variables. So how? Let's see. If we have x dot y dot z, if we complement entire term, it's equal to x bar plus y bar plus z bar. Okay, so we changed all here in this part. For this part, we changed and to all, and then complemented each of the variables. And the same thing here, if we have x plus y plus z, if we complement this function, this term, it's equal to x bar dot y bar dot z bar. Okay, it's very important. The next theorem, which is the last theorem, is called Law of Elimination. Theorem number 5. which is the law of elimination. Okay, and it says that x plus x bar y is equal to x plus y, and x dot x bar plus y is equal to x y. So these are laws of elimination. So we're done with postulates and theorems. Now I will tell you about the precedence of operations. So if we have a function including all and, all, and not gate, which of them should be performed first? So it's simple. So we say what is precedence of operations. First of all, if we have a parenthesis, anything inside the parenthesis should be performed first, because parenthesis has the highest priority. But if there is no parenthesis, we have some orders in it. So here I say in parenthesis can be used to indicate the order in which the operations should be performed. In the absence of parentheses, the operations must be performed in the order not, and then all. So not has highest priority, then and then all. So here is an example. Let's say we have x1 dot x2 plus x1 bar dot x2 bar. So first we need to perform the not, so x bar, x1 bar and x2 bar, then and functions. So we need to perform x1, x2, and x1 bar, x2 bar, and finally we perform the all. So x1 dot x2 plus x1 bar dot x2 bar. Okay, so this one is the order of function. Okay, in the next lecture, I will talk about building the functions by combining the different gates.